The motion of a rocket in real life is quite complex. The data set that we're going to be working with here today was collected from not a real large-scale rocket. It was collected from a toy rocket. We can see that at the start of the clock, there was no force acting on the rocket. After 0.04 seconds, the thrust became 2 newtons in the upward direction. Now, that's just an upward force, this thrust. It doesn't take into account the net force. Then after 0.08 seconds, the force increased more, and it just kept going up from there until we get to the maximum force here, around 0.32 seconds. I can zoom in on this. That's where it got to be the very largest force. After that, the force started decreasing, actually. Maybe the rocket started running out of fuel, perhaps. And the force keeps decreasing until eventually force stops completely after 1.76 seconds from the start of the launch. All right, now we can graph this force versus time if we want. We could select both the time and the thrust. Now we should be able to insert a scatter plot here. If we just do insert, you can click on right here, XY scatter. And there we get a nice picture of the force. As we can see, the force is quite variable. So now that we have that, we could change our title, thrust versus time. There's this add chart element, axis titles. We want time in seconds for that. Then we'll do primary vertical. And let's change this to the thrust in newtons. Now it says here, we have to take into account the fact that the mass of the rocket is going to decrease as the fuel burns. It also says there will be substantial drag forces. We already dealt with that in previous lab. So this is just going to be a continuation of that. And it would be true of model rockets as well as full-scale rockets. We're going to create a mathematical model that incorporates all these aspects of the motion that could all be changing at the same time. We'll start with a very simplified model of just constant thrust, constant mass, and no drag. And then we'll gradually eliminate these simplifications, arriving at a much more complex and realistic model. All right, so in this activity, our mass of our model rocket is 230 grams, but it initially carries 25 grams of fuel. So the total initial mass of the system is 255 grams. And the rocket begins at rest on the ground, of course. You're going to want to use either OpenOffice or Microsoft Excel. You can download Apache OpenOffice for free. Okay, so we're going to create a graph of thrust versus time. We just did that. Now the first model that we're going to try is, let's pretend that the thrust is constant. If you take a look at the graph, we're going to be looking for, is there a graph we could make that's kind of similar to this graph, except that it's just one force value instead of a change in force value. So what do I mean? I mean, let's take a look at the real graph. And it's got all these snapshots of different force values, right? So, here the force is like, 4 newtons there. And here it's like 18 newtons. And over here it's like 15 newtons, always changing. But what I'm going to propose is that there is some average value to this graph. An average value somewhere around here, where if it were to hold that force for the whole interval, then that could be similar in the behavior to the real situation. And so, one of Sir Isaac Newton's great insights into physics and mathematics was that the area under the curve has meaning. And so what Newton would say is that if you take the area under this graph and calculate it, then it has a physics meaning. So what are the units that we're dealing with in this problem, right? So we've got force in newtons on the vertical. We've got time in seconds on the horizontal. Now that area there is going to be called J, which is the impulse. The area here is the impulse delivered by the thrust. Now, it's not a net impulse because there's also the weight of the rocket to consider as well. But yeah, we're going to have J. It has a formula, force times time, right? As long as the force is constant. And so what Newton would argue is that we could come up with a constant force where if it held that particular force, like an average force, for a certain time, t total, then that area could potentially have the same area as the curved one. That's what Newton would say. So there's some average force which will end up having the same effect on the rocket that the changing force would have had. So now F is an average force for the 1.76 second interval. Okay, now, how do we find that? Well, we want to use the procedure they talk about here. So, what they're saying here is if we were to add up all the forces that act on the rocket, like the upward thrusts there, and multiply them by some tiny change in time, then what we'd be getting is we'd be getting little rectangles here. And this would be like an approximation of the area. And so each one has a height of F, and it's going to have a width of a little delta t. So that would be like just one contribution to the impulse right there. All right? That's what that says. And what they're saying is that if we did that here, it would be the same as just multiplying the average force times the total time. That's what it says. So let's see. What's the next one say? We should do a weighted average where we multiply our forces times our times and then divide by the total interval time. That would be the weighted average formula for finding this value, this average force. Okay, so let's see if we can do that. It tells us on the next, they're saying you go to your Excel file, and to get the impulse, you could simply just multiply straight across. Like I could let this cell C14 equal the force times the delta t. So with that in mind, we could multiply the B14 times just B $10. So what I'm doing there is I'm calling up this time step cell. This time step cell is something that I could always edit later if I want. See, if I just type in 0.04, then I'd have to go through and edit each cell later if I ever wanted to change the time step, you know. So here I'm just going to multiply by $10. That locks it in on that cell. Yeah, you can't type C for it. You just have to type equals. So equals B14 times $10. Okay, so yeah, you got to do like a control click and then go to format cells if you want to get a different precision. See, I've set mine to 4 decimal places. You know, you could do more or less. Keep in mind that what the lab is saying is that I kind of used a simplification that I would use the initial thrust, like at the start of the delta t, as if it was the thrust for that whole time. So what I would be creating would be called, sometimes it's called a left sum. Or if you really want to get precise with it, they're saying that if you use the data from 0 to 0.4, try to find the average force for that interval. It's not a big deal if you don't. It's going to come out similar, but you know, they're saying that instead of just calling up B14, I could call up an average of B14 and B15 because that's going to be the next force, and then just divide them by 2. And so now the force that it's going to use is actually going to be 1 Newton because that's the average of these two forces. So maybe just for simplicity's sake, I'll just leave it as a left sum for now. It doesn't matter to me if you leave it as a left sum. Totally fine. Just a little simpler. Okay, next, let's see. We want to determine what is the total sum of all these little impulses. Okay, so just go to the bottom of your column of the impulses and just sum that column up. So we want to do a sum. We can go from C14 to C58. You can also click and drag, like if you just do sum and then just go up there, select this one, drag it down. You know, I'll write that down here. Sigma means the sum from time of 0 to the end of the interval. That's what that means. Of our force. I'm going to use like the initial force times delta t. Mine came out to 20.016. The units will be Newton seconds because we are multiplying a force times a time. Just out of curiosity, if I do switch it to what they asked for, you know, just for completeness here, if I use what's called the what they're calling the average force for the interval, let's see what that comes out to. It would be that slightly different way of calculating where I get an average of B14 and B15. And then just drag that down. It should propagate all the way through. 20.016. So pretty much the same thing. It didn't end up making any difference. So, okay. All right, so we got our total impulse. Now let's go and see if we can calculate the average force for the whole interval. Okay, so all we have to do is take our value from above, and then we'll divide by the total time. So that's going to be 20.016 Newton seconds divide by 1.76 seconds. Okay. I get 11.373. Newton seconds divided by seconds makes newtons, which is an average force. We want a value between 11 and 12. Okay, so we're good to go. Now it says find the maximum height by hand. So it says we got the 255-gram rocket. It's launched vertically upward from rest. The thrust acting on the rocket is, we're going to pretend, equal to just the 11.4 newtons. I'm going to say that at first we're going to have the rocket at rest on the ground, and it's going to start to feel an upward force, which I'll call this F bar of thrust. Now, not only does it have that, but it also has its own weight too. We got to take that into account. Now, at some point, the force stops. Once the force stops, the thing is only going to feel its own weight at that point. Let's say the thrust ends. And then when we get to the peak, we're just going to feel its own weight still. It's in free fall. All right, so what is this interval here? There's constant thrust. But here, as it sails up to its peak, it's now in free fall. So let's let that thrust be 11.4 newtons. We should calculate the weight of the thing, be an mg, so that's 0.255 kilograms times g. Remember, we're pretending like the rocket has the same mass the whole time now. I get 2.499 newtons. I suppose event 1 could be start of the clock. Event 2 is thrust stops. Event 3 is we've now reached the peak. So our start of our launch is, of course, going to happen at t equals 0. R stands for the displacement of the thing. We haven't gone anywhere yet, so let's call that 0. And we are just starting to turn that upward thrust on, so let's let that velocity be 0 as well. But we should calculate the acceleration during the constant thrust interval. They're calling that A12 because this is 0.1, this is 0.2, this is 0.3. So when we're going from 1 to 2, we should do the net force on the rocket divided by the mass of the rocket. That's going to be an upward 11.4 newtons, and then basically 2.50, and we'll divide by the mass, 0.255. Alright, so we get that acceleration. It's 8.87 newtons net divided by 0.255, 34.0 1.78 meters per second squared then. All right, so let's write that in. Now our thrust stops. We know the answer to how long that takes. 1.76 seconds. How far does it go though? So let's just use motion formula for that right now. So how far does it go? I'd use this formula, that the delta y would be 1/2 AYT squared plus VIYT. That's just a standard motion formula from the past. We have everything that we would need to plug into this. Okay, there we go. 53.9 meters is how far it goes. All right, so we can put that in here. For our final velocity, we could use the formula delta V equals A times delta T. We know the acceleration here. It's 34.78. It lasts for 1.76 seconds, so our delta V would be 61.2 meters per second. Let's put that here. And then our acceleration in the next interval, they're talking about this interval here, A23 would be just negative 9.8 at that time. Because it's in free fall, between 1 and 2, we found an acceleration of 34.78. That was in the positive direction. All right, then. So yeah, what would be the time that it takes to reach the peak? Now, I'm going to assume free fall from this point on. And we could do just, here's a little graph of it. If we do position versus time, a rocket will accelerate in the upward direction, reaching a maximum speed. Then the thrust stops. And at that point, it should go on to make this trajectory where it finally reaches the peak. And then it would come down in a parabolic fashion until hitting the ground. Alright, so our acceleration here was 34. Our acceleration here is negative 9.8. So let's use this formula. Delta Vy is going to be the acceleration times the delta t. Alright, so this is the delta t that we're interested in right now, between point 2 and point 3. This is, of course, point 1, point 2, point 3. That's what we're trying to find, is how long does it take? We know the delta v, though, that's going to happen. It's going to be a v final minus a v initial. Alright, so what is the final velocity? That's up here. Our v final for the interval has to be 0. When you get to the peak, you got a velocity of 0 in the y direction. For here, our initial velocity for this interval was claimed to be 61.2 meters per second. Okay, so we just have to plug the values in now. 0 minus 61.2 equals negative 9.8 times delta t. We'll solve for it. 6.246 seconds. This first delta t, that was 1.76 seconds. So, okay, we got to add these two together then. 8 seconds even. Takes 8 total seconds to reach the peak. All right, now, how high does it get off ground? We got to find this out. How tall is that? All right, so we could find the delta y for that second interval of going from 2 to 3, and then just add it to the delta y that we had calculated earlier. All right, so what do we need for that? We need 1/2 ay t squared plus viyt. That would work. So it's going to be 1/2 negative 9.8, 6.246 seconds. But don't forget, we also have to start off with an initial velocity here. Our initial velocity for this interval is 61.2 meters per second. And just put in that delta t. All right, that should be our calculation then. I'm getting 191.1 meters. That is in addition to the 53.9 that we already traveled during the thrust phase. So we're going to want to add them two together so that we get the total height. So peak height, 53.9 meters plus 191 meters. That's 0.1. Yep, takes us to 245 meters total. All right. And final velocity, of course, just 0 at the peak. Yeah, so let's see if we can get the spreadsheet now to agree with what we've calculated. Now we're going to need some more columns. So we're going to have thrust force. And this is going to be just a constant thrust model, which is not the real situation, right? But what we do is we just use that 11.3727. All right, so I copied the constant force all the way down. I want a column for the weight of my rocket. We calculated that before. It was 0.2499 newtons. 2.49, okay. Okay, I'm going to put the units in. Newtons. This is newtons as well. We want the net force next. That's going to be a subtraction of J14 minus K14. Just like we calculated earlier. Upward force of 8.87 newtons on this rocket. Got the net force. Now that we have the net force, let's go to the acceleration next. So for this, and we can write in what the formulas are if we want, like just, this is thrust minus weight. That's how we calculate the net force. For the acceleration, we just want A equals F net divided by the mass. That's going to be the formula we'll use. All right, so let's do L14 divided by the rocket mass. Now, somewhere in the spreadsheet, we have the rocket mass, 0.23 for the rocket itself, and then 0.025 for the fuel. So I'll just add them two together, B6 plus B7. All right, so we'll get L14 divided by the sum of $6 plus $7. So now I'll just drag that down. We should find just a nice constant acceleration the whole time. And that is the value we calculated for that. Now let's get the velocity. You know, we could, if we wanted, use the formula that V at any given time is going to be the acceleration times the elapsed time, because it's a constant acceleration. But what would be better for building our spreadsheet, something we can use in the future, would be to let the new velocity be equal to the old velocity plus whatever the acceleration was at that old time times delta t. So what is the meaning of this? The new velocity and calculating it by adding the old velocity plus the old acceleration times the delta t, or the time step. So that's the formula we'd ideally like to enter into the spreadsheet. It would be better for us to use this. All right, so let's see if we can do it maybe both ways here just for a second. All right, first, if we were just doing a simple a times t, we would do m14 times the elapsed time of a14. This would be a fairly simplistic approach. And look at those values, like they are in agreement with what we found by the calculations. We said that the velocity would increase from 0 up to a max of around 61.2 meters per second. That was shown right here in our calculations. All right, so that's just one way to do it, but the better way is this second way. Okay, so let's try it that way now. Start off with the second cell, because you want to use the first cell in your calculation. We're going to do old velocity, or maybe call it previous velocity. Okay, so previous velocity plus previous acceleration times delta t. That is our goal. So, okay, start with the second one, because we wouldn't know what the original velocity was if we didn't start with the second one. So now I'm going to go equals n14 plus m14 times my time step. And instead of just typing in 0.04, I'll go and reference the B10. B10 has my time step saved. So that way, if I just make that one change later, I can change everything around. Yeah, there we go. I can just copy and drag that down. And we want to see that these values are identical, because it's constant acceleration. All right, so far so good. Now we just want a position column, and we just want to use the same approach that the r of t would have been given by like 1/2 a t squared plus vi t. But what we're going to use instead is that the new position equals the old position plus whatever the velocity was a moment ago times our delta t. So new position equals the old position plus the old velocity times the time step. Same concept. Previous position plus previous velocity times delta t. All right, we're starting off on the ground at rest. Then our next position will equal the old position, which is 014, plus previous velocity, I'll call that up from n14, times my time step of $10, going back to referencing it from here. There we go. Now we should be able to drag that down. So the thing about the spreadsheet, because we're doing it incrementally like this, like in reality this motion is continuous, but we are doing an approximation of it, which is not quite the reality. And so there's going to be what I refer to as like a lag. It's close to where it should be, but it takes like a little bit for the spreadsheet to kind of catch up, because it's calculating on old values and acting like they're the value the whole time when they're not. Yeah. So, okay. But it will be a close approximation. Let's see. Did the values line up? I believe it did. I saw it got to a height of around 50 something. This one says if it was perfect calculation, it'd be 53.9. The spreadsheet says 52.6, which is pretty close to what the formulas would say. So yeah, so far so good. Now it says, based on the spreadsheet, determine the maximum height reached by this rocket and how long does it take. So I only really did the first step of the piecewise function. The piecewise function here, it's like an upward opening parabola. That's all I modeled so far with the spreadsheet. And I got up to this height of around 53 or 54. But now we want to go all the way to the peak. So let's see what it takes to do that. Go back to the spreadsheet. We just want to let that acceleration change. At some point, there's an important point where the acceleration now drops to a new value. It drops to g, so negative 9.8. I think there's a g, here of 9.8, so I can just call up that b9. We want it to be negative though, and then let it continue to be negative 9.8 from then on. But of course the weight of the object won't change. And in fact, an even better way of getting those values would be to base them on the forces involved. So we're going to let that thrust drop to 0, because we ran out of fuel. Let the weight continue to be 2.499. And now we'll just carry this calculation down to thrust minus the weight. After a certain time, 1.76 seconds, we run out of fuel. And this upward 11.3 was all due to the fuel pushing it upward. But this is 1.76 seconds after that initial launch. That's when that thrust has to run out. That's what we showed in this diagram. The thrust is going with a nice 11.4 until we get to this point. Thrust suddenly drops off. Okay, cool. So now we see that our net force has now become negative. I could now just let the acceleration be calculated based on that net force now. Then I'm going to just drag down this column because it's still going to calculate it based on the accelerations. So, okay, our velocity starts to go down, once the thrust is removed, basically. And so I didn't even make it really long enough to get to the peak. We need that velocity to go all the way to 0 so that we're really at the peak. So I got to drag a lot more columns down. Yeah, so an important point that we're looking for here is right here. This is where that velocity goes to 0. So this really must be the peak of this motion. Carry our position calculation down, see how high this thing goes. It gets up to around a maximum value of 256.5. That's approximately the peak. You could argue this one might be the peak because it's the highest position value. And that's when the velocity is closest to 0, so I'll shift it down, that's fine. Great. So is that in agreement with what we calculated by the formulas? Somewhat. I had said 245 was how high it would go. Spreadsheet says 256. So what's the reason for the discrepancy? It's because the delta t is somewhat large. So there's going to be a little bit of error in the spreadsheet. 0.04 is a fairly large delta t. Okay, so let's see what they ask next. It says, compare these values. If they're not extremely close, could you correct the problem? There is a way to correct it. We just want to change our delta t. So let's see if we could do that. I'm going to change it now to 0.02. See if everything propagates through now. A problem there is that we have to go longer, because if I make a column here for elapsed time, I would just do like 0 there. Let's do the previous time, like J14 plus $10. So I'm trying to get like clock values here from the start of the launch. So the problem is we can see that we can't really cut off the thrust here at 0.88. That's not valid. See, we've got to go farther. We've got to go all the way to 1.76. All right, so I'm just going to copy this down until we get to 1.76 now. Then we'll cut off the thrust. Okay, that's good. Okay, as we can see, our velocity has not gone to 0 yet. So this is not the peak anymore. So we want to go all the way till we get to around 0. That's right around here. And look what happened. Now we're having a height off ground of 250, which is better. Before it said 256, which is like way too high. And let's see if we could go just even farther, just change that delta t maybe to a 0.01. If we do that, we have to just make the necessary adjustments. Got to go to 1.76 with the thrust. And we're going to have to move our peak once again. But let's copy everything down. See if we can get an even more precise result. Now it looks like our peak is around 248. So you can see, yeah, it's just getting better and better the more we shrink that delta t down. So that's really good there. They're extremely close, just like they asked. Okay. Now, what if we let the thrust now be variable? What would that require? We're going to still let the mass be constant, but now instead of letting that thrust always be the 11.37, let's let it vary. What I'm going to do is I'm going to switch, I guess I got to switch back to the 0.04 because we only really have thrust for those time steps. So I'm just going to switch back real quick. But we get the theory that the smaller the time step is, the better. All right, let's get rid of this. Move our peak back. Yeah, we got to drop off the force after 1.76 seconds. Our peak is back here again. And also, it would be good just to make a graph. Let's make a graph of the position versus time. So if we could just select. All right, so drag that down. I'm going to go not just to the peak, but I'm going to go even farther just to see where it hits ground. Let that position come back to 0. All right, we can call it position versus time. Okay, then we just got to do it again. Let's do velocity versus time. And I'm just hitting command, holding command while I select on Mac. Insert scatter plot. Okay, beautiful graph. Okay, so that gives us a real good sense of what has happened here with the rocket. Now I'm going to copy that whole thing and just make a little change. You may have to adjust the calculations when you do copy. So this is supposed to reference B6, not V6. And this guy, AH times B14. Okay, so that's a copy of what we had before. Now this is not going to be a constant thrust model. This is going to be variable thrust model. I'm going to just change the thrust. Change the thrust to these values which they gave. So let's copy those. Does this affect the peak? It says, based on the actual variation, do you think the model will fly higher, lower, or the same as your original? Way back at the start of all this, remember Newton? Newton says that if you have an average force applied constantly for a certain time interval, it could potentially have the same area and the same impulse as if a changing force were applied for that same time interval. As long as the areas are the same, Newton would say the impulses would be the same. Hopefully the same. Yeah, hopefully we'll get the same kind of results as we did the other way. Let's check it out. Look for the peak. The very highest point. It occurs at around 253.869. This is the peak. Similar? Pretty similar. 256, 253. The difference is probably just due to the inherent error in the spreadsheet calculation. It's just an approximation. Now let's do variable mass. First, I'm going to make my graphs, though. Okay, there we go. Now let's copy everything we have. Variable force, variable mass. Here they're saying we want the mass to decrease, but proportionally to the impulse of the step is what they're saying. I just want to solve it for the mass lost each step. If I solve it, I get they're saying total mass lost over total impulse times impulse of each step. Delta M equals a difference between the 255 grams minus, so if I were to substitute in, so 20.016, okay. This is the mass lost divided by 20.016 times our F delta T. We could come up with a new bunch of formulas. So a mass lost each step, total mass lost, total mass, because that's what you want ultimately. All right, so for the mass lost each step, we were going to take the 0.025, which is $7, and we were going to make a proportion where you multiply by the impulse lost that step, which would be the force AN14 times the delta T of $10, and then divide by that total impulse delivered of 20.016, which I could call it up from the proper column here, C60. Now it's going to give us just a little bit of mass lost each step until eventually you stop losing mass. Okay, now if that formula is put in right, then our total mass could be a sum of all the masses that were lost here. I could just add them up. We'd have 0 there. So start with 0 and then add the mass lost right here. And whatever you lose there just goes into the total. And then for that next step, you take the previous mass that you had, AP15, and add in the next increment that was lost. And hopefully this is all going to add up to 0.025 lost. So the formulas I used were 0.025 times this ratio of F delta T divided by the 20.016. That's what I did there. And then here for the mass lost, I just did previous mass lost plus mass lost in current step. Let's see if it works out. It works out perfectly. Wow, okay. Yeah, we get right up to 0.025 lost after the whole thing is done. That's pretty cool. Okay. Now we can just let it propagate through. We shouldn't really have to change much. We have to calculate the total rocket mass, which will be found by, we start with this 0.255. We'll now want to just take that and subtract the amount that's been lost. So I would do minus a AP 14, and then just copy that all the way down. And we can see how our rocket mass goes from the largest that it will ever be, 0.255, all the way down to 0.23. Yeah, so perfect. Okay. They want us to determine the new height reached by the rocket. Oh, we do have to include a weight calculation. Okay, weight of rocket. W equals mg. So take AQ14, multiply it by G, which was B9. Alright, got the weight back. Now we just have to alter this force so that it calculates it on the weight there. So the net force is going to be the thrust, AN14 minus the weight, which is AR14. Copy that down. This looks pretty good. We're just looking for that highest peak. And would it go higher? It does. It goes all the way up to 281.99. This is our new peak. It's not surprising that it goes higher because the rocket would have less mass. According to this model, it used to only go to 253 because it was heavier. Now it's lighter. Alright, so that's pretty cool. Let's see, they also want drag included. Alright, so now we're going to include drag. Using this formula, that the drag force can be given by negative BV times the absolute value of V. They mean for a sign to be included there. When I write this formula, personally, I put a little Y on there. This could be positive or negative, depending on the situation. Because when your rocket is going up, if the velocity is up, then the drag force is against you. So this is when Vy is positive. We need the drag force to be negative. If the rocket were on the way down and the velocity was this way, now the drag force would be upward. So I just put a Y on there to make it clear that it could be positive or negative. So I'll put that into my formula. Alright, so let's see if we can add an extra column for this drag force, and then we're done. I could copy everything over, just add in one more column of drag. So when it comes to the net force, we want thrust minus weight plus the F drag. I'll insert a column for F drag in the Y dimension. So this can be positive or negative. The formula is negative B times Vy times the absolute value of Vy. Now there's a B that they give us to be 3 times 10 to the minus 4. Oh, it's already there. It's row B8. We'll call it up. So let's do equals, we need negative $B$8, which is the drag coefficient, times the current velocity, which is going to be BP14, that's this here, and then we'll do times the absolute value, ABS, of BP14. That should do it. I'll carry that down. That looks good. We see how the drag force is getting larger in size as the rocket begins to move. And let's drag it all the way down. And all right, let's see if our drag force makes sense. We do want the drag to reach a maximum when the velocity is at a maximum. So right around here, with 62.2 is the maximum speed. That is also the largest drag force in the negative direction, slowing the rocket down. Then the drag force goes down until we get toward the peak. At the peak, the drag force should go to 0 because that is where the velocity is 0. I didn't figure in the drag force into the net force yet. Okay. So now let's figure in the drag. We have to do not only BH14 minus BL14, we have to also add BM14. Now that includes the drag force into the net force. Notice that our peak now occurs at 223.1 right here. So a significant decrease in the altitude that the rocket goes to. We also see an interesting thing that the net force heads towards 0 as time goes on, so it's approaching a terminal velocity. You can let that go even farther. We should see if we carry it down. Yeah, we want that net force to end up heading toward a zero, which means terminal velocity is being reached, which is pretty cool. Let's try to just plot it and see what we can see. If we could see some of the features of the terminal velocity here, because it's going to go up like the others did, but as it heads down, we're supposed to see it go linear. That means drag's being included. So that is cool. We'll just do the same thing here with velocity. The velocity goes to, just a horizontal over time. So that's the terminal velocity there, negative 86 or so. And finally, one more. Acceleration should go to 0 over time. There we go. Perfect view of terminal velocity being reached.